Today's webinar is Wildfire Threat Data in Action, a community level perspective. So we will definitely be kind of feeding off of our last webinar and drilling in a little bit deeper. My name is Nicholas Sovril, and I'm a registered professional forester. I am a co-owner and founder of Frontera. I am here with Holden Payne, who is our wildfire analyst at Frontera. And I'm also here with Jean-Simon Michaud, who is a senior geomatics specialist at Hatfield. Frontera is a top-notch forestry, wildfire, and field management consulting company, and we work quite a bit in BC, but we have other projects across Canada. And Hatfield is a leading environmental consultancy based in North Vancouver, providing multidisciplinary services in environmental and social sciences. So this webinar is co-hosted by both Frontera and Hatfield. So we're excited to kind of share some time and space and tell folks what we're working on together. I would like to acknowledge that the Frontera and the Hatfield offices are located on the traditional and unceded territories of the Squamish and Tsleil-Waututh nations, also known colonially as the City of North Vancouver, British Columbia. Housekeeping items. Very obvious, but we are using Google Meet. If you may have an issue or that sort of thing, maybe type it in. We have somebody out on our side that's taking in requests for help, that kind of thing. We are actively recording right now, and we will be putting the recording up on the Frontera YouTube channel. So so you're aware. And we'd ask that everybody mute themselves until the final 30 minutes or the question and answer session. However, for sure, we'd like folks to leave questions or comments in the chat box. You should all be able to do that. And then at the final 30 minutes, we'll take those questions and comments kind of in the order that they were received, in that chronological order. We were also happy to take questions, oral questions as well. Like we did in webinar 1, we want to use and will be using Poll Everywhere, which is it's a technology that just allows for active live digital polling. We have about 5 Poll Everywheres in the presentation, and yeah, we really think the polls will help kind of brighten up the presentation, and then also kind of allow all of us to see and understand a bit better who our audience is. So I think it'll just help the presentation. To use the Poll Everywhere, just use the QR code on your screen. If that doesn't work, then you can use the pollev.com/Nicholas Sovril 633. That will also work. For those folks that are doing that, why don't we test it now? Because we're gonna do 2 Poll Everywheres to get things going. At the prompt, just put your name in, and a little plug here: we are not recording the Poll Everywhere information. It will get erased after the webinar. All right, so the first Poll Everywhere question for everybody: what category best describes your profession? And I did my best at kind of building bigger kind of professions in here. I'm going to make this live. Great, we got some polls coming in. I'll give folks some time so we can get a sense for where people work. Oh, we've got a lot of others. If anybody wants to put in the chat box what their others are, that would be helpful. I actually can't see the chat box right now, so if Oben, anything comes up there that is of interest.
Yeah, nothing yet regarding people's professions. We just have a comment from Jessica suggesting that we use the Q&A feature when people are asking questions. That way we can check them off and people can upvote them.
Okay. All right. Looks like at least there's quite a few others. Not sure what that exactly means, but yeah, we've got about 20% academic researcher, and then a split between wildland fire and forestry silviculture range. And then, yeah, so pretty good spread. Next, poll everywhere. So you can kind of, this should pop up on your phone. Did you attend Frontera's webinar #1? So I put yes, no, or I watched the YouTube video, because that's kind of like the, also a yes, but a little different. So this will also help us understand if essentially just what kind of background folks have on what we're talking about. It's not required that you saw webinar #1. This is just better information to have. So that's okay. That's good to know. About 2/3 is nope. The numbers are switching. It's about half and half now. Okay, excellent. It's really helpful. Okay, so let's get into goals of the webinar. So as I said before, this is the second part of a 2-part webinar series. Our webinar #1 was titled BC Wildfire Threat Modeling, Introducing an Exciting New Provincial Data Set, which again, we have a recording of that. That's on our YouTube channel right here, which we will add to the chat box, so you can save that for later. In webinar #1, we outlined our threat modeling data sets that are at the provincial level, went through the methods on how we did that, what the data sets are, and also the an accuracy assessment of what we have so far, and also kind of a call for engagement for all of you. So that was, I think, a really successful webinar 1. And in this webinar, we're going to kind of feed off of that. We're going to essentially look at the provincial data that we talked about in webinar #1, but zoom into the resort municipality of Whistler area and Whistler's surrounding Cheakamus Community Forest, or the CCF. So we'll go through the provincial data and then kind of go through those data sets to just try to get an understanding of how that data can be used, and how we actually are at Frontera. We're using that data to help Whistler's wildfire resiliency projects and work. And then we'll transition into fire model visualizations, and then we will hear from Jean-Simon from Hatfield, who will present on Arbosense solutions, and then we'll kind of feed that back into the integration into other fire models. I'll breeze through this agenda. So after I speak here, Holden will take the microphone, and he will go over kind of a review of webinar #1, just a refresher. Then we'll go into the Whistler level data. Then we'll talk about wildfire pathways and our visualizations, switching over to Jean-Simon, and then we'll kind of round off things with final modeling, and then I'll come back in and kind of lead us into the question and answer session. So without further ado, I will pass this over to you, Holden, and I will exit out of my presentation.
Thanks, Nick. Okay, let's jump straight into it. Yeah, so as Nick said, we'll start off, well, as Nick said, my name is Holden. Yeah, excited to talk to you guys all today about some of the stuff we've been working on, particularly how we can translate kind of some big data that we produced in webinar 1, so our big burn probability modeling, over to kind of more local data, and how we can use that to plan for wildfire risk reduction, fuel management plans, CBORPs, anything under the sun as it relates to kind of how you plan for local fire dynamics. So I'm glad that about like half of y'all, it seemed like, had gone to webinar 1. For those who were not there, hopefully this review is helpful. I'm going to try to skim through it a little bit so that we don't spend too much time talking about what we had, but basically what we produced at Frontera over a year now is essentially wildfire threat for all of British Columbia. So we did this using a large burn probability simulation model, burned over 5,000 iterations. The model is called Burn P3, and essentially burns a bunch of fires over kind of idealized fire seasons, and then aggregates that data up to the landscape scale. And we built this model kind of with the goal of improving predicting fire risk, predicting fire threat for BC, and particularly predicting fire threat for BC and relativizing it, so we can plan for fire threat up in the northeast and compare it to fire threat down in the Kamloops or the southern interior, or fire threat in the Chilcotin. And in webinar 1, we talked about accuracy and how we built all of it. And so if you're interested in that, go back, rewatch that YouTube video. So We won't dive into that too much, but I will dive into kind of what we do have from webinar 1, which is really, really great data products and great fire behavior kind of data and analysis on all of British Columbia. So on the left, we have burn probability. In the center, we have rate of spread. And then on the right, we have head fire intensity. And this is kind of our 3-weighted threat equation that Frontera likes to use to predict wildfire threat. The most important of those being burn probability. So where are fires most likely to occur? Not necessarily start, but where they're most likely to just burn through. So that could be starting there and burning somewhere else, or starting somewhere else and burning there. And then rate of spread, how fast do fires move? And then fire intensity, how intense are those fires? And then that tells us quite a bit about how likely we are to suppress them. So if we bring those all together, it gives us a really good idea of threat at the provincial level. And this webinar, kind of the goal of this is how can we use that data and then localize it? Can it be applied kind of at a local scale to projects? Is it accurate at pretty fine scale? Because we do have fine data, like the data is at 100 meter by 100 meter resolution all across the province, which is great. But do those trends that we see and the accuracy that we found at the provincial level, do they hold up when we work at the community level? And I think that we're finding with this is that they do. And so this is our threat kind of map for BC, and we're working on getting a kind of a more usable, available version of this up soon. And also, looking for people interested in using it, helping them with their projects or their community. And the good thing about kind of the way we've gone about doing this is that it's not just kind of a one-stop shop for, a flat raster scene that tells us threatened areas in BC. We can also pull out the data at the local scale and look at local fire and environment data. So from that, we can get our fire perimeter. So where did the fires actually burn at the local level? Like in your specific valley, what fires burned and which way did they spread? How fast did they move? That can tell you about trigger points for when you need to be concerned about certain types of fire behavior that's, specific to your area. And then also what type of fire behavior you should expect for your area. On top of that, we can get ignition density. So where are ignitions happening on our landscape? Do we match the patterns we kind of expect to see in a particular area? And also what type of ignitions are we getting? Are they human or are they lightning? And what does that tell you for fire risk? If you're planning for a lightning ignition versus a human ignition, you probably need to consider different factors. And so with this data, the good part about this process and using big simulation models is that you can pull all the ins and outs of the model and get a lot more data out of it than kind of just your static wildfire threat or burn probability. I already talked about spread directions, but that's one of the big ones that we think is really cool. And then also local driving fire weather patterns. So those could be those trigger points, but also like what in your area is driving your fire behavior. So is it weather? Is it fuels? Is it topography? If it's fuels, what type of fuel types are you getting the worst fire behavior? And then if it's weather, under what weather conditions, what wind speeds, what directions, all that good stuff can be pulled out. And so I'm kind of talking about this stuff because I want us to go from now the landscape scale of BC all the way down to kind of the community scale, so a particular valley, a particular watershed or something. And to do that, we are going to go down into Whistler and particularly the work that we've done with the CCF, because I think it's a great, it's a really great community to be working in. It's also one that, Frontera has been working with Whistler for a couple of years now. So I think it's a perfect example of, how we localize this type of data and how we use kind of models that were built at the big scale, but then, applied locally. So the first concept that we want to get across is a fireshed concept, which has been talked about for a little while in fire ecology now, but I think started really getting some traction in the last couple of years. And so what is a fireshed? Really simply from a kind of fire analysis and fire modeling perspective, it's an aggregate of all potential fire perimeters into your community of interest. But it's an ecological concept. The idea is if you are capturing fire dynamics well in your particular region, that any fires that intersect either your community center, like we have here, or your community WUI, whatever you care about, those are kind of the areas or a domain of interest where you start to be concerned about fire spread. So if I'm a person living in this community center, I need to be worried about all the fires or all the area of land around me in this area, and past it. As long as my model is good, past it, I don't necessarily need to concern myself with it as much because I know it's just much less likely that a fire spreads from that direction. And so it helps, one, expand out kind of the area of interest. So we're planning for an appropriate ecological domain. We're not just planning for the WUI. We're thinking about the broader landscapes because fires can move fast and they can grow really quickly. I think on the coast, like the Alejo fire is a great example of or Elaho is a great example of just a fire that ripped really, really quickly. And hopefully if we capture those types of extreme events, we know what to prepare for. But it also doesn't make you go too far. Landscapes can feel really, really big and they are huge. And we don't want to get bogged down with thinking about every threatened area under the sun around a community or what if it comes from here or not. So this concept is one that we really like to use, and I in particular think is really, really useful for planning. So Whistler's Fireshed, which will pop up right here, is just an aggregate of this is just we'll show you kind of the particular community later on, but this is an aggregate of all the fires that were burned in the model for the Whistler area. So we pull them all out, and then we can merge them all together and create this nice outline to tell us, okay, this is kind of your new planning horizon. This is where we need to essentially concern ourselves with areas, with forest areas. And in this case, we intersect them with the WUI because we want to concern ourselves kind of with the edge of the WUI. Excuse me. But you can intersect them with your community points. You can intersect them with your structure. You can kind of decide how you want to build your fireshed, but we like to build it off the WUI. And the good part about this fireshed analysis is also it kind of helps provide a template upon which you should analyze the rest of your data. So your burn probability should be analyzed in the context of that particular fireshed. So you know where in your area of interest, are fires more likely or less likely. And then your rates of spread and your head fire intensity and your threat are all in the context of that fireshed. So I know to plan for threat within that area. You can contextualize threat in the broader landscape like we have with our provincial model, but you don't want to get bogged down with, the idea that, threat is so low in my area compared to maybe the southern interior, but you still have threat in your area, and you got to figure out, how do you manage your particular threat? And so planning for your fireshed, I think, is the kind of the best way to do that. So Whistler's Fireshed, we found kind of as we did a bunch of analysis on this, some interesting things that drive Whistler's Fireshed. Particularly, we did some analysis for the CCF on climate change's impacts on fire regime dynamics. So we modeled Whistler under a bunch of different climate scenarios, which is a pretty cool project. And we found that as you increase, the climate impacts on fire weather, we find that it grows longer and more linear. So this is like kind of the regular fireshed, but the kind of expanded firesheds grow longer and more linear as you have fire behavior driven more by extreme wind and also by outflow events that kind of drive wind through the valleys, which anyone who's worked in Whistler knows is kind of a concern. We also find human conditions drive a lot of fire behavior here, which is not that concerning. Whistler is a very popular place for recreating and, lots of people moving through every day, and a lot of growth upslope. So humid conditions in the valley bottoms linked to roads or linked to recreation or even like harvesting regimes, and then growth upslope. We also found that kind of what's interesting about Whistler is because of its built up environment, particularly the ski slopes, eastern side fire growth was kind of limited by both the WUI and the ski resort fuel conditions. The fireshed is kind of lopsided to the left, in part because there was just less growth on the right side because of the mountain, frankly. And so that's kind of an interesting thing that, we were able to capture those dynamics. Whereas in the Northwest, fire areas were much less limited. So we had much bigger fires up in this area, in part because, those fire regimes are not limited by some of these built up environments. And kind of our takeaway here is that fire spread dynamics into Whistler communities are limited by some of those built up environments, ski slopes, big roads, Highway 99, but that spotting is particularly still kind of a really high concern, and also outflow events remain the worst case scenarios. And then in Whistler in particular, how does that translate into emergency management? Because there's kind of just that one highway out of there. How do we think about that in the context of what's the most risky or the most threatening fire behavior for this landscape? So contextualizing our local landscape from the model, from kind of the provincial model, we were able to pull out for Whistler, our fire behavior, so our rate of spread and our head fire intensity. We can find, how fast fires are moving, and then how intense those fires that are there. We can also pull out our burn probability. So, this is scaled to a maximum as we like to look at it for the fireshed. So where is the highest potential for fire in your fireshed and from those areas? We could also pull out our fire perimeters and spread patterns. We could pull out those individual perimeters and look at them and say, under what conditions did these start and where did these things go? And then, how can we mitigate them, or what are we going to do about them? And then aggregate all that data up into our wildfire threat to look at what's the most threatened places in Whistler, and then what type of fire behavior are we going to expect there, and then, what can we do about it from there? So now I'm going to dive over to our interactive map of Whistler's landscape. So I'll just take a second. Yeah, so let's go straight into our burn probability map. So this is just a burn probability map of Whistler. That red outline is Whistler's fireshed. So for this analysis, you can see areas of elevated burn probability. The scale is just normalized to the maximum. So 1 would just be the worst area in Whistler's fireshed, 0 being the least bad area. And we can see areas of particularly the Callahan Valley, going up to Rainbow Mountain, and then on the east side of Rainbow Mountain and in the Cougar Mountain area where we have areas of elevated burn probability. And again, burn probability could be, either a fire like a fire convergence point, so a bunch of fires are converging in those areas, or it could be a bunch of fires are starting and going somewhere else. So you have to think about that as well when interpreting burn probability. Yeah, this is not too big of a landscape, so I don't want to spend too much time here because we have a lot to go through. But on top of that, we can also pull out the 90th percentile rate of spread. So these are just classed from some Arcane rate of spread classes correlating to significant types of rates of spread groups. And the cell values for these are the aggregates of all of the fires that burn. So we're actually pulling out all the fires that burned over those cells and saying how fast did all those fires move in those cells. And then we're pulling out the 90th percentile of those rates of spread. And we're seeing trends that we would expect that are similar from what happened with burn probability. So elevated rates of spread, particularly in steeper areas going to the Callahan Valley, up slopes of Rainbow and Mount Sprout, and then up on even on the slopes of Blackcomb Mountain as well. Also, and down in the this section of Callahan Valley furthermore. And then we also have headfire intensity. So these are also classed by kind of typical Red Book headfire intensity classes. So our ranks, and then I added an extra one just kind of for ease of interpretation. But I think the important thing to look at here and for fire planning, even for suppression planning, is that we want to look at fires that are kind of rank 3 and below, because those are areas where direct attack and suppression can be very effective. So that's 2,000 kilowatts and below. So that would be kind of the light yellow. And then the greens, those are areas where we know that, we can be pretty successful in suppressing. And above that, we start to have more action on the fire. We start to have much more intensity, torching of trees, engagement of the canopy, and potential for suppression to be ineffective. And also for spread dynamics to be out of control. So that's when we also have, potential for long range spotting, which can lead to, consumption of homes and then spreading into communities. And so using headfire intensity as well, we can isolate areas where, okay, maybe we need to think about more aggressive treatments, or when our treatments maybe not going to work as well. And we need to think about, emergency management plans, like, elevated headfire intensity up in the Callahan means we need to think about, very particularly about how our treatments might be affected. But yeah, these are just examples of kind of the 3 input layers that we use to generate our wildfire threat. And then we can go into our wildfire threat here and try to isolate areas where all those 3 converge to tell us that, this particular area is uniquely threatened from wildfire. So these classes are we like to split into 4 classes that do kind of depend on your landscape. You might want to play around with how your classes are used depending on where you are in BC. But we have kind of low to moderate, I would say mostly moderate threat, which we think is consistent for this area, particularly kind of in the transition between the coast and the interior. Elevated, so high and extreme threat in the Callahan Valley area, as well as in Rainbow Mountain and Cougar Mountain, which is consistent with kind of, if anyone's worked in Whistler, kind of what I think people might expect out of wildfire threat. And the good part about kind of looking at this data at the local level is that we can also compare it to other data that we have, particularly the PSTA for this area, which is frequently used for figuring out about your wildfire threat in a particular area and for designing a treatment or thinking about what type of planning you might do under CWRP. And the same classes were used for both of these. You can compare it, and you can also see how the PSTA method has significantly elevated threat all across the Whistler landscape. So extreme to high threat in a lot of these places that maybe probably are not extreme to high threat, especially in parts of kind of transitional coastal zones, but also maybe is homogeneizing threat in a way that's not as useful for where we can actually isolate stands that we might want to be able to do some work. But yeah, feel free to look at those for a second while I get us back over to the main PowerPoint. Great.
Holden, you are a little over time, probably about 5 minutes, but
thanks. So yeah, let's just do a poll everywhere. Let's do clear responses. Have you guys talk. So a lot of people, I'm assuming, particularly if you're working in the forestry consulting space or also in the wildfire risk reduction space, do work with the PSDA, and as do we. And so we want to know, does the PSDA threat data at the moment provide you with sufficient data to confidently complete wildfire threat and risk assessments? Does it tell you kind of where areas of high threat are, and is it useful to y'all? So if we could start getting some responses there. Not really. Okay. 100% for not really. Moderately yes. Moderately yes. good that we're not seeing not at all, not really and moderately yeses. Yeah, that's good. Okay, yeah, it seems like a pretty good mixture of that. And that I think is kind of most of our experience with using it is it can sometimes be kind of homogeneizing if everywhere is considered a high threat, but certainly useful in picking out particular stands also because it is field type based. So we would expect it to be pretty good at that. Let's move on though. And so the kind of how we want to build upon one, taking the data from the provincial level down to the local level, which we just did in generating fire sheds. And then how can those fire sheds, help us determine particular treatments or a better plan for fire threat in their areas. And we can do that with predicting fire spread corridors. So this is a method that we've been working with for a couple months now. It was developed in 2024 by a paper by Wang and others, people at the CFS and NRCan, and they did a really, really good job in using rate of spread in your landscape within your fire shed to predict a particular wildfire pathway. So this helps you predict what is the fastest pathway for a fire to move into your community. And as I'm talking about this, you look at that graphic on the right is just one of our kind of final products of of major pathways into Whistler. And this was built a little bit different because Frontera modifies that approach and uses, instead of rate of spread, we use burn probability as the cost layer. So instead of finding the fastest pathway from any area in your fire shed into Whistler, we're going to say, where is the most likely pathway, which we think is a little bit more useful for planning, particularly as you're trying to connect areas of higher burn probability to areas of your community. So how do we establish almost like an exposure method, like some of the kind of the approach that Jen Beverly and others are working on, but maybe a little bit more discrete. And this approach, both of ours and the Wang approach, uses a least cost distance concept from anywhere in your fire shed to a focal point in your community. And you can use one focal point or two or three or four, and you can also scale them if you wanted to. So you could, decide, I could, train this approach to pick a focal point that is most like relevant to me by distance or by access or whatever it is. And so steps to doing this, we're going to go over it a little bit, probably not dive too deep because it can get complicated, but very basically, this method is pretty cool. It sees ignitions in every cell in your fire shed. So you want to work within the domain of where you're concerned. And so in this case for Whistler, we're going to seed over 70,000 ignitions in Whistler. And then we're going to ask those ignitions, how would you get to areas of the community that we're concerned about? And what's the most likely path for you to do it? We also change that algorithm to account for things like slope and predominant wind direction so that fires are usually not choosing to like spread down slope. We adjust for those things to try to get the kind of spread corridors as accurately as possible. And by seeding an ignition in every single cell, we're considering all possible spread patterns and vectors. So everywhere in the landscape on 100 meter by 100 meter, we're asking how would you get from that point to areas in Whistler that we're concerned about. And this approach then uses those seeded fire shed ignition points and Dijkstra's algorithm to predict the shortest path into your community points. And for Frontera's method, burn probability is that cost layer. So we're asking, your agent to find a way through the community or through the forest using areas of high burn probability as your vectors. And you should choose your focus points in your community based on, areas you're concerned about, and then also ask how an area of high burn probability would connect to your community. And that generates those fire pathways. So basically what we've gone from is those seeded ignitions into these blue pathways. And we can see it's kind of tree-like, and we've kind of simplified it here for visual, but really there's a pathway in every single cell. And as you can see, it converges around areas of high burn probability, because in this method, we're looking for corridors or major areas of high burn probability. And then to get to corridors, we can aggregate those pathways up. We can take those pathways and look for density and say, okay, now that we know all the possible pathways, are there any similar trends? Are there valleys that it likes to move through? Are there slopes it likes to move across? Are there areas where it likes to converge and then enter a community together? And this will help with landscape planning, right? Because if we have a big landscape and a big fire shed, we can isolate particular areas based on regions we know to be concerning, and then say, okay, how will a fire move through here? And then what can we do to mitigate it? So we can, essentially we're asking, the model to isolate connections between high burn probability and your community. And, similar to an exposure metric. And so the percentage here on the right is just percentage of total pathways. So, the blue lines will be 1 to 5%, purple 5 to 10, 10 to 20, and then those orange and yellow lines are 20 to 35, and then 35 to 50%. Of total ignitions in Whistler. So we have kind of the biggest pathways in kind of this area and the south of or east of the Callahan and kind of the Cheakamus Crossing area. And then up here around kind of Cougar and Rainbow Mountain, Wedge Mount area, we have another major pathway. And from there, we can, kind of analyze our pathway density and decide, okay, what do we want to actually focus on? Like, what is a pathway that's concerning? What type of fire is going to move through this area? And then what can we do about it? Especially if we have a big landscape like Whistler. So from there, let's take this map of our fireshed and our kind of major pathways and then zoom into a particular pathway. So one of the biggest ones we found was kind of this Callahan and Cheakamus crossing area, where we found that there was a major pathway. And so we can zoom in on that pathway and say, okay, what are we actually going to do about it there? And so now applying that to fuel management, we can see this is a map of the pathway, the major pathway, kind of the biggest in Whistler, overlaid over wildfire threat rating, and then also potential blocks that we developed in our work with the CCF. And this, these pathways can be useful in assisting in finer scale fuel treatment design. So like location, where do we want to put treatments? Now that we know that this is kind of a major corridor, where do we want to put our treatments? How do we want to orient those treatments? What is the treatment purpose? Are they trying to just reduce fire behavior? Are they used as anchor points? Are these access treatments? And then also scenario testing. We can rerun these pathways given different treatments and see what it does to potential pathways. And the benefit, I think, about essentially what we've gone from is provincial level data down to landscape level data down to a particular valley or slope level data for actual treatment design, and can now isolate like particular fire behavior dynamics at the landscape, at the slope level. So are fires going to, come across and jump the Callahan Valley? Perhaps are they likely to start kind of off the Callahan Valley Road and rip up the slope? And then maybe a risk to this area is spotting or potential for a cross slope spread rather than necessarily down and across a highway. And so these were essentially trying to bring both, big scale models down to really, really local level to say, what are the particular fire dynamics at this level? And then how do we design treatment that's around them? So to make sure that these pathways are cut off, how do we make sure that we remove the exposure between areas of high burn probability and then areas of the community that we're worried about? So after that, I guess I want to ask you all, how interested in some of these wildfire visualizations are you guys for your community or your landscape? Do they seem useful? And do people think, these approaches could aid in, I think, isolating, but also making sense of kind of big landscapes, particularly with like a lot of changing and increasingly severe wildfire behavior that is harder and harder to predict in some cases. We want to take big landscapes and then make them piecemeal so we can actually understand them in ways that are both calling upon local knowledge, but also modeled data and modeled knowledge. Good responses, very much and interested. I like to see that. And so we're kind of going to switch gears really quickly here now that we've talked about this. And these are all kind of fuel type based models. So Burn P3 is built on fuel typing and, has quite a few other parameters that we tune based on fire weather and other things, but fuel typing is kind of the underpinning of Burn P3 and comes with drawbacks. And I think everyone here knows that, particularly after webinar 1, there was a lot of discussion around fuel typing. And so within a modeling framework, fuels have, the utmost important, and accuracy is crucial. And we already have some concerns with both provincial and federal fuel typing layers. So because of that, we've been collaborating with Hatfield to produce, test, and develop kind of better ways to look at forest structural changes and also forest structural components to predict fire behavior a little bit more accurately, to get away from the fuel typing component so that we can redo some of these approaches like predicting wildfire threat and maybe pathways, but using on the ground forest structural components rather than fuels that, contain some errors. So I will turn it over to Jean-Jamon now, and he's going to talk about what Hatfield has been working on.
Great. Thank you, Holden. Thank you, Nick. It's been a pretty good introduction to what I'm going to be talking next. Let me just try to get my slides over here. Just bear with me for a second. Somehow the share button doesn't seem to work here. Just hold on for a second. Okay, here we go.
We should get some elevator music while we're waiting for this.
Yeah, sorry
Every
for that.
transition, just click the music. No, no problem.
Yeah, can you see my screen now?
Yes, yes.
Okay, let me go into slideshow mode. There we go. Okay, how's that looking?
Looking good.
Yeah, you can see it properly.
Yes.
Okay, excellent. All right, so I guess I'll first start with a question. So why does community scale fuels data matter? So really, fuels are highly variable at a community scale, and especially in the wildland urban interface environments. So we know that existing fuel type layers that are often used are based on vegetation inventory data, which can be outdated and not always represent the fuel condition accurately. And field work or field validation to verify these fuel layers can be costly, time-consuming, and is necessarily spatially limited. And this is where ArborSense Fuels is slotting in. So over the next few slides, I'll be presenting ArborSense Fuel, which is a solution that leverages remote sensing technologies to provide fuel information that better represents the current canopy and understory structure to support wildfire behavior modeling and local decision making. So a bit of an overview here. The ArborSense Solutions is funded by Innovative Solutions Canada, and this funding was put in place to support the development of advanced tools that help wildfire practitioners better characterize local and regional wildfire risk conditions that are relevant to community wildfire risk. And the research behind this solution has been ongoing since 2023. So we're collaborating with Dr. Laura Chasmer, Dr. Chris Hopkinson, and the Western University research team, and together in partnership with Frontera Forest Solutions. So ArborSense Fuels, really the main two needs that we're trying to address with ArborSense Fuels is to generate mapping products that will address first the current FBP system fuel type classes, and second, generate structural and compositional attribute maps that can be used for advanced modeling, like the modeling that Frontera is doing. And there are multiple benefits to getting this type of information. So first, it provides improved spatial detail and representation of fuel structure. It provides a faster update cycle to better reflect the underground conditions, and it unlocks the use of detailed fuel attributes and fuel types that can be used in advanced data-driven wildfire modeling, and thus reducing the reliance on static provincial fuel classification. And now we will get into what data support the solution. So ArborSense Fuels is really relying on an extensive set of data. So we are leveraging data that is acquired over 6 ecozones in Western Canada. So we have over 200 ground plots, over 30 UAV or remotely piloted aircraft system surveys, collecting both LiDAR and multispectral data. We have more than 10,000 square kilometers of ALS coverage, and then for all these ecozones, we have wall-to-wall coverage using open satellite imagery. And it's important to say that models were developed per ecozone and adapted by forest type, topography, and climate context. So then the question becomes, how are these data sources combined together? Excuse me. So really, ArborSense Fuel is a multi-scale approach. So we use an approach that nests these complementary technologies. So it really integrates the field data, the RPAS, the ALS data, and satellite data, and it leverages the strength of each data source, and it enables us to scale from plot data all the way to the community level. And as mentioned earlier, this approach is able to support both the FBP fuel type layers and then doing direct estimation and modeling of fuel attributes. Now, building on this, we will go into a little more detail of how we apply the solution specifically to the Whistler case. First, starting with the field work. So we conducted, Frontera conducted some field work. Over 60 ground plots were collected over 6 different areas in the resort municipality of Whistler. And for each plot, stand and fuel structure attributes were collected, as well as stand density and composition, and surface and ground fuels. And this field data was used for supporting our modeling of fuel typing and structural fuel attributes. And then now I'm going to jump into the fuel typing approach. So here I'm discussing a little bit how ArborSense Fuels is our approach through using remote sensing to enhance the fuel typing layers. So it is developed really using forest structural and compositional attributes. And in this way, it captures the variability not represented in layers derived from photo-interpreted vegetation inventories. It integrates the spectral information and detect differences in vegetation condition and fuel characteristics at a finer spatial scales. And it can provide a more detailed and consistent representation of fuel condition. And necessarily, this supports more reliable wildfire behavior modeling, fuel management planning, and threat assessments. So the approach is really leveraging the current approach to fuel typing. So we're using the expert-informed decision on fuel typing. So in this specific case, we're in BC, so we're leveraging the Perkis et al. 2018 research, and we're using that information to feed into the ArborSense fuel model, and together with Sentinel-2 imagery. From that Sentinel-2 multispectral data, we derive some spectral information, so both vegetation indices and some spectral bands. And we have ALS LiDAR data where, together with the field, the ground data, the field measurements, we're able to measure structural and compositional attributes. So we model those, feed that into the ArborSense fuel typing model, and together with the expert decision tree that I was referring to, then we're able to create the validated ArborSense fuel type maps that we validate, again, using the field validation from Frontera. And here is a visual of the output for the region of Whistler. What is important to say is that this map is a preliminary result. So we have yet to validate it from the field data that we obtained from Frontera. So this is really just fresh off the press, and I wanted to show some early results just to give you a sense of how it comes through. But if you're interested in learning more about this, then necessarily you can reach out to me, and we can keep you updated about how we're progressing with the validation of our layer here. So now that we've concluded the fuel typing section of the presentation, I'll jump into more of the structural fuel attributes. So the second portion of my talk. And So ArborSense fuels can generate multiple attributes, multiple structural attributes. So really from LiDAR point clouds, we measure directly canopy height, canopy cover, and using our advanced modeling, we're able to model canopy base height, canopy fuel load, bulk density, and basal area. And if we go a little bit deeper into how does it work, so really we're using point cloud data, and from this LiDAR point cloud data, we derive some point cloud metrics like max height, height percentiles, kurtulces, and others, and those directly can inform on the canopy height and canopy cover. And separately, these point cloud metrics can feed into our fuel attribute models together with ground fuel plot data, and these are used to create the or to model the canopy base height, fuel load, bulk density, and basal area. And the output is these gridded map of fuel attributes at various spatial resolution. So in the next slide, I'll show an example of the result of CBH, so the canopy base height at the scale of Whistler. So here, what you see on the left-hand side is a scatter plot that shows for each plot location that we had in Whistler, what was the predicted value on the y-axis and the observed value at this location. And you can see that there's a fairly good agreement with what we predicted from the modeling using LiDAR and ArborSense fuels compared to what was observed in the field. And here is it takes a bit of time to load, but here is a visual of the distribution of the canopy base height. So it ranges roughly from 0 to 12 meters. And there's quite a bit of variability throughout the resort municipality of Whistler. I will not go through too much detail on this because I know Holden will be covering some of these differences in the next few slides. But yeah, I guess here I will slowly pass it over to Holden. So I think he'll be able to demonstrate the direct use of these attributes in his advanced modeling and how he can integrate that into fire landscape threat tool that they've been working on.
Great, thanks. Okay. Is my screen up there, everyone?
Not yet. There it is.
There we go. Okay, great. So thank you, Jean-Simon. And then now I want to talk, hopefully somewhat briefly, about how we can integrate some of those layers that Hatfield is working on into some more advanced and kind of new and unique models that we're using here to better assess both conditions on the ground and then also how fire weather and fire behavior kind of interact in these scenarios to predict fire threat. So integrating ArborSense into fire behavior modeling now. So to do this, we're working with a new model that was actually developed here in Frontera. So that's the fire landscape threat tool. And we've been working on it for a little over 2 years now, and it integrates physical fuel structural data. So getting away from fuel types and actually using data on the ground. So that's, surface fuel loads on the ground if we have them, and then also, canopy fuels that ArborSense produces with empirical and semi-physical fire behavior models. And hopefully this approach can get away from some of the errors that are connected to fuel typing and also better predict really, really fine scale. So not just, block level or like polygon level, but fine scale raster cell level alterations in fire behavior linked to both changes in fire weather with topography, but also, changes to fire behavior with fuel structures. One of the benefits to kind of the ArborSense output is that it's super, super fine. I mean, we have data at the 10-meter scale. So we're capturing variations in CBH, bulk density, and fuels that, are really, really fine. And you can also see how fire behavior might interplay with that. One of the benefits to this model, and one of the reasons we developed it, is that it also uses heterogeneous weather data. So we have a harmonized downscaled climate and station data set that produces smooth surfaces of weather. So every 10-meter resolution, we have changes in wind speed, changes in wind behavior, direction. We have fine field moisture, temperature, relative humidity. So all of those interplays between topography and weather, rather than just station data that's a valley away. We have it interpolated across the surface on your landscape, so we can actually see how changes in weather are going to impact fire behavior at pretty fine scales, which is pretty cool. It's a non-spread model, so we're not modeling fire spread. We're modeling fire threat or fire risk at a particular point in your landscape, linked to the potential for fire behavior, the potential for crown fire activity, ignition potential, and a couple of other things. It removes that fuel typing error, as I talked about. We're getting away from those fuel type groups. And it links multiple models. It's a pretty expansive model, and I'll give you a bit of a flow chart of how it works in the next slide without diving too deep, because there's a lot under the hood, but it's iterative. So we run over hundreds to thousands of weather events. So we're not just capturing 90th percentile, we're capturing extreme weather events where, maybe RH is 30, but temperature is 10, and maybe fine field moisture is 10%, but RH is a little higher, or all these different components that might affect fire behavior in different ways. We're not just predicting extreme across the board, but different ranges of weather events. It also includes wind modeling, so we're predicting dynamic wind and terrain feedback. So we're getting smooth and interpolated wind across the landscape, and then in-stand behavior. So relative humidity, temperature, and fine field moisture are all modeled within 4 stands. And all of those will feed into our surface and crown fire behavior models that are linked to predict potential for extreme fire activity. So this is kind of a general overview of the fire landscape threat tool. Fundamentally, it's an extreme fire behavior prediction model. Like I said, it uses fine scale and heterogeneous weather. And then the best part of it is it uses forest structural components. So we're actually getting at the characteristics of forest that affect surface and crown fire behavior, particularly that canopy base height, because we know that from both physical fire behavior models and empirical ones is a crucial component for predicting the likelihood of extreme fire activity as it relates to intense surface fires on the ground jumping up into the crown. That's really kind of what we're concerned about, especially when planning, for certain things like fuel treatments. And so we have kind of 2 mechanisms for building those canopy fuels. We have the ArborSense, which is the new method, and then we have the old method, which is a series of canopy stand models that are VRI derived. And I'll get into kind of those 2 distinctions here and why we think ArborSense improves our tool quite a bit, because it improves our ability to predict in-stand canopy characteristics. So that old method is VRI based, which may or may not be up to date, and is also linked to harvesting regimes, when was this block last actioned on, and whether we have good data or not. And the new method is fully smoothed across the landscape at really, really fine scales, and based on accurate field data, and also ALS, or also LiDAR and satellite imagery. And so applying ArborSense to our landscape, we can look at what we used to do, which is kind of that VRI approach. We have our original canopy base height metric across the Whistler landscape, including the CCF and RMOW. We can see that existing canopy stand prediction models overestimate CBH. We're getting those yellow classes all over Whistler, which is 10+ meters CBH, and the maximum is like 34 meters CBH, which is really, really high for a lot of these stands in Whistler. We have over 60 study plots in the area, so we know it's high from the study plots, but I also know anyone who's walked in Whistler probably knows 10+ meter CBH all over the place is quite a bit higher than what actually happens on the ground. And it's built on kind of some weaker relationships with data, and then also old and outdated VRI data. And so that's why we're really excited about using new and updated data, and also field verified data. And the result of that is that we get poor assessments of forest structure. We're not actually capturing those dynamics of forest structure at the valley level or at the stand level that we need to predict fire behavior well, which is why we have to rely on field types, because we don't have those forest structural data sets. But now with ArborSense, we do. And the new ArborSense improved CBH layer gives us better accuracy of forest fields. So now we have 0 to 1 and 1 to 3 meter CBH across much of the CCF, which is much more consistent with what we would expect for these types of forests, especially with those kind of lower canopy cedars and firs. And you can also see how ArborSense picks up trends in the landscape linked to structural components like riparian areas where maybe you have more old growth and there wasn't logging, or fuel treatments as well. And we can also touch upon that last fact, the fuel treatment fact, by zooming in on this part of the landscape, again, back to the Callahan that we like to talk about so much today. So if we zoom in on the Callahan, we can look at some study plots that we, Frontera, have there, and also a fuel treatment that was done between 2015 and 2018. And so this is the original canopy base, kind of the VRI based model. You can see much of the area of this part of the Callahan is in the 10 plus meter class, really high CVH. And then it actually does a pretty good job of picking up that fuel treatment, in part because the VRI was updated with it. But it predicts the fuel treatment to have lower CVH than the surrounding forest matrix, 6 to 10 meters or 3 to 6 rather than 10 plus, which is usually not how we expect fuel treatments to behave in context of the surrounding forest matrix. They usually have higher CVH, especially as we prune them compared to most of our other forests here. But if we look at what ArborSense predicts, we can find ArborSense captures those dynamics well. The rest of the forest matrix in the Callahan has significantly lower CVH, 0 to 1 and 1 to 3 meters, whereas our fuel treatments, not only does it capture, one, the pruning that we've done in these treatments, but two, it also captures variability in them, areas where we left gaps and we have actually really, really high CVH. So something like that, or areas where we didn't treat. This was an untreated area. You can see that the CVH is down to 1 because we didn't treat in there and we didn't prune. And so ArborSense captured all of those dynamics at really, really fine scale, which is really cool to see, because then we can apply those physical and structural components to better and better models and then predict fire behavior much more accurately and at finer scales. And I think the fuel treatment component is a big benefit to this, because in the past, it's hard to integrate fuel treatments into fire risk and threat modeling because we just don't have the modeling framework to capture how changes to fuel treatments will change fire behavior. But now with physical structural data, we do, because now we can run these into fire behavior model and see, are our fuel treatments working the way that they are without just a static change from, say a C4 to a C7 or something that we know doesn't really capture the dynamics of fuel treatments accurately. And so we can apply those results and then produce kind of a similar threat, but different threat map through FLTT. So this is the Fire Landscape Threat Tools threat map, which is produced a little differently than the threat map we showed you above, but with a kind of similar approach in the area. And we can see how using the original VRI-based canopy base height, we get our FLTT wildfire threat with mostly low to moderate threat across the landscape, mostly low and a little bit of areas of high and, kind of no extreme threat in the area. But if we apply our improved ArborSense based fuels with our better canopy base height, where ArborSense predicts canopy base heights are significantly lower across our landscape, we can then reapply our threat tool and see that particularly under extreme conditions, which FLTT runs under, wildfire threat is moderate to high across much of Whistler, which is a lot more consistent with the type of fire behavior we would expect in these landscapes. And if we compare the two, you can see how FLTT with ArborSense, I'm just switching back and forth between the original here and then the improved version, we can see how it fills in those areas and predicts not only higher threat, but more specific high threat and moderate across the landscape under these conditions. And it also captures dynamics that we captured in the threat tool above better. We see better agreement between this approach with ArborSense, where we have elevated areas of threat in the Callahan and up here at the base of Rainbow and Cougar Mountain that we didn't get with the original approach. So ArborSense is now improving our threat tool from FLTT and agreeing with the other method that we were using above. So both of our modeling methods agreeing that at the local level, these are areas of elevated threat and maybe areas where, we should be concerned about mitigation. And I'm going to pass it off to Nick for takeaways.
Thank you, Holden. You're pretty much exactly on time, so isn't that fantastic? Thank you very much, Holden. Thank you very much, Jean-Simon. I want to ask everybody now, maybe switch gears, quite a bit of technical information there and hopefully some exciting conversation that we'll have. But before we get there, I wanted to ask the audience, are you interested in using these model outputs for your project? At the last webinar, we asked for kind of a call for questions after the webinar and really wanted to kind of engage with our larger forestry wildfire community and just learn what the needs are from you all. At this point, Frontera, we're ready to really start hopefully either selling the data, or we also have kind of an offer here that I'll go over. But in terms of contact or asking questions and or potential purchasing, please contact me. My email is info@fronterasolutions.ca. And if you have questions or you want more information about ArborSense fuels and the Hatfield solution, please contact Jean-Simon Michaud at Michaud at hatfieldgroup.com. On the Frontera side, yes, we are now selling the provincial Burn P3 data sets. So those data sets include the fire threat data set, which is a combination of burn probability, rate of spread, and head fire intensity. That's available for all of British Columbia. And then in that data, we also have trigger point information. So kind of the causal factors behind why those rasters or those areas have that predicted fire behavior, which is essentially a form of metadata. So if you are interested in getting data for your community, contact me and you'd like to buy it, great. In terms of the fire pathway information that you learned about, we can produce fire pathways using the provincial Burn P3 data sets. That's sort of a separate request, but that can be done as well. So that's sort of a separate but similar request. Now, before we get into Q&A, I wanted to also make an offer to all you folks. We are also offering for really a limited time to those people that maybe aren't really ready to purchase or want to test the data for their community, contact me. We're ready to clip an AOI of your community and send that to you, and then answer questions or provide some kind of support if you'd like, so that you can kind of test the data before you potentially purchase. Again, contact me at info@frontierasolutions.ca for any of that. I think at this point we are definitely ready for question and answer. And I think, Oben, are you still available?
I am, yep. I'm here, and we've got a couple of questions queued up in the Q&A section. I invite anybody who may still have questions. It's not too late. You can drop them in Q&A or just in the regular chat. We'll start with Jessica's question, which was, what weighting did you give to each of your 3 threat components?
Holden, do you want to answer that? I can go back to that slide too.
Yeah, sure. Yeah, it's a pretty simple weighting scheme. It's like a weighted sum. Burn probability is the highest, so it's 0.4 for burn probability, and then 0.35 for rate of spread, and then 0.25 for head fire intensity. Sorry, opposite way around. 0.25 for rate of spread, 0.35 for head fire intensity. We want to capture where fire is most likely first, and then how intense they are, which more linked to suppression, and then how fast they move.
Can you go over that maybe just a little, just again, in terms of weighting? Burn probability is?
Burn probability is ranked the highest. So 40% of our threat score comes from burn probability, because we want to capture where fires are coming from mostly. And then 35% comes from head fire intensity. We want to capture how intense those fires are. Likelihood of suppression is much more closely linked to that. And then rate of spread, how fast they move, is 25%.
Hopefully, Jessica, that answers your question. I think that was
great. Thank you.
no problem.
Right on. Next, we had an anonymous question posted. Are fire pathways based on the direction of spread from the head of the fire, or is flanking fire movement, for example, also factored in here?
Got it. Okay. Yeah, fire pathways are based on, I guess it would be, the concept is not necessarily really like as an individual fire moving through the landscape. It's more if a fire were to follow, or an agent were to follow kind of areas of high burn probability, which kind of corridors would it take? I wouldn't think of it as a fire, because you're not regrowing a fire. But the model outputs that go into predicting burn probability and rate of spread in Burn P3 are always head fire outputs in Burn P3. And so you could think of it as head fire more than think of it as flanking fire movement. We have another method that does actually kind of grow fires and look at those fire paths, and that also uses head fire. So we're usually not considering flanking fire in these instances, but it would be an interesting approach.
If that person wants to, I think that was an anonymous question and answer, but if they want to follow up with another question, I think that's fine.
Yeah, if anyone asks a question and then I'm answering and you just turn your mic off and respond, feel free to.
Okay, for now, I'll just move on to another question from Kyle. He asks, could you describe how the heterogeneous weather surface models work in FLTT?
Yeah, so it integrates a couple of models. So first and foremost, it takes ERA 5 land surfaces. So that's the land reanalysis data sets as far back as I think we're using 30 years of data right now to kind of characterize wildfire behavior across our landscape. And then essentially what we do is we filter for extreme fire weather days. So now we're pulling extreme fire weather days. We're pulling those kind of smooth weather surfaces, and then we're downscaling them to the resolution that we want from that data, and then modifying it by station observations. So we're integrating both station data and harmonized and climate downscale data to produce smooth surfaces that are, we think, more accurate. The downscale climate data is good, but it has limitations. Like under extreme events, we don't actually always capture some of those extreme wind events. So that's why we're using station data to modify that to make sure we capture on a particular day, what does the downscale data say and what does the station say, and then how do we harmonize it and downscale it using terrain and elevation modifiers. And then those also feed into other models like predicting in-stand temperature, relative humidity, and then also fine fuel moisture, that on top of the wind modeling. So it's kind of like 3 or 4 models that all come together to produce these smooth surfaces. I hope that answers the question without going into crazy detail, but I hope I tried to get that, Kyle.
Yeah, no, that was great. Thank you. Just wondering, how does that differ from the provincial model that you elaborated on in the last webinar?
Yeah, good question. That's different because what Burn P3 does is essentially creates fire weather zones. And so when a fire in the model of Burn P3 grows, it pulls from your list of weather in your weather zone. In your weather zone, we use kind of like the they're called weather zones. They're linked to kind of the BEC data that BCWS produces or the Ministry of Forest produces. And so any fire that starts within that weather zone will get that data. And if your weather zones are accurate and the stations are accurate, it can be pretty good. But also stations tend to be around airports. They tend to be more exposed, or maybe they're in a valley over. And so the difference with that is you're essentially just pulling station data for all the fires that grow in that area. Whereas here, we're actually getting some at least more accurate modifications to wind, weather, fine fuel moisture linked to terrain and specific climate dynamics in that area. If that makes sense.
Yeah, that's super helpful. Thank you.
Mm-hmm.
Okay, I've got a new question from Valerie. For ArboSense, how well are your surface models performing? Is there a reason that this uses the burn hour values rather than provincial standard fuel loads?
Excuse me.
I don't know. That might be a question for Jean Simon. Yeah, sorry.
So I'm not entirely sure I understood the question very well. So Valerie is referring to the surface fuel load. So that does that refer to fuel typing? Oh, Valerie, if you can unmute and explain a little bit your question, that'd be great.
Hi, sorry, it's Sadie, not Valerie. We're just sharing the same Zoom call. This may have not been ArboSense then. Yeah, so talking about fuel typing of how well the surface fuels models are performing and why it's 100-hour or 1,000-hour burn time rather than like a coarse woody debris or fine woody debris that provincial fuel standards use.
Would that be a question for you, Holden? Because I'm not.
It might be. I'm actually confused as to where.
It sounds like, is it surface fuel consumption that you're asking about?
Yeah, was that your question, Sadie?
Fuels?
So it was part of the fuel typing. Yeah, I have something. Talking about like the Paracas et al., the 2018 fuel typing standards. I just saw like a 100-hour, 1,000-hour burn time, which is a standard that like the US uses, or is more commonly used in like European surface fuel models, where in BC and Alberta, it's usually like a fuel load, it's like a kilogram per meter squared. So I was just wondering it was in one of the slides. I was just wondering if there's a reason why like a time or a burn time was being used rather than a weighted fuel load.
Yeah, okay, I get your question, Valerie. Nick, if you go back up to the fieldwork slide, this is where we talk about the different hour of burn time, and this is data that was collected by Frontera in the field. On our side at Hatfield, we're really focusing on fuel types following the Paracas approach. So really following quite closely the decision tree, the parameters behind the decision tree. So we're not necessarily using these the time of burn referred here.
I can I think I get what you're asking. Also, that's so the 1, 10, and 100-hour classes are just classes of fuel. So we do actually use the load. We're not using the time. That's just how you classify them. So it'd be like, how much kilograms do you have of 1 hour fuels, which are fuels that take an hour to reach, 66% of moisture content or whatever. And you can use kind of the BCWS classes or the US classes and just lump them together if you want to in your fine fuel models. But it's not the actual time, it is the load of those classes.
Yeah, thank you. Just like in provincials, we talk about like fuel classes by diameter. So it's like fine woody debris is under 7 centimeters of diameter, and then over 7 centimeters is coarse woody debris. So they're both fuel loads. I was just wondering if you just chose the methodology of Paracas, and that's fine. I was just wondering if there was a particular reason or choice of why it was these like hour fuel loads rather than the fine and coarse woody debris standards.
Yes. It ends up being the same thing. Like if you run a part of the surface fire behavior model we use in FLTT uses an American fire behavior model, which splits it into those groups. But the less than 7 centimeters is pretty much the same as saying 1s, 10s, and 100s. I mean, there's a little bit of like, you have to do some finagling around the numbers, but so that's why we were specific about those 3 classes. But I think we are talking about the same thing.
Yeah. More questions?
Yeah, great. We have a question from Kapil. Is this model benchmarked against any existing model or real data? He believes he missed that part if it was mentioned in the webinar.
Which model is he referring to from the presentation?
Good question. That's not explicitly mentioned. Kapil, do you want to chime in?
I could probably just answer for both of them. At least, I mean, Arbosense is benchmarked against like field measured data like we have here. That's how Arbosense is built. And if John Simone wants to add more that I missed, the provincial model and the provincial threat was benchmarked against actual fire history. So we did a ton of accuracy testing on all fires across British Columbia. We also broke it down by ecoregion. So we tested to make sure that the types of fires we would expect in the model are also happening, or that we'd expect in real life are also happening in the model, and the accuracy was pretty good across most of BC. And then FLTT, that one has not been benchmarked or tested. Testing wildfire threat is tricky because you have to find some way to verify a threat on the ground. So I think testing the model is closer to like, does the model align with your expectations of fire behavior in that area? So yeah, short answer to that would be no for FLTT.
Yeah, and not too much more to add on Arbosense. We're just benchmarking against the field data that was collected.
Okay, great. Those are all the questions we have in the Q&A section. If anybody has any final questions, they're welcome to chime in now.
Sorry, I just had a quick one here. Just wondering about the downsampling that happens with the resolution. I guess that's so you can go from the higher res down to that 10 meter.
Yes. Yeah. Sorry. If that's questions for me. Yeah. We don't necessarily downsample all the way down to 10 meter for our weather data. That would be, I think, a little outside of our possibility. Like predicting like weather from ERA 5 level down to 10 meter doesn't make a ton of sense, but we'll go closer. I forget our full resolution, but I think it's closer to like 100 to 500 meter for weather. So we're assuming that, weather in the 100 to 500 meter cell on anywhere your landscape is the same, which is pretty consistent depending on kind of your terrain and where you are. We don't want to downsample the 10 meters, if that makes sense.
Yeah, I gotcha. And otherwise, like the resolution was, I guess it just varies based on the attributes then.
It would vary. Yeah, it would vary by the attributes. Since we have ArborSense really fine at 10 meters, we produce the outputs at 10 meters, which we think is good. But if you don't have ArborSense that fine, or you don't have fuel structural data that fine, then you don't need to produce it at that level. And it should vary by your landscape. If you expect more for structural variability, maybe you have more finer detail, but you don't also want to go too fine because you're capturing changes that don't really exist. But for this scale, I think the 10 meter worked really well, especially as it picked up those fuel type changes or structural changes linked to the fuel treatments. The fact that it captured treated and untreated really nicely means that was probably a good resolution to pick, and that's why ArborSense is so cool.
Yeah, awesome.
Thanks for the question. Any other questions? If there are no more questions, and everybody's hopefully been quite engaged out there, great. And as I said previously, go ahead and contact me at info@Frontier Solutions or Jean-Simon at jsmichaud@hatfieldgroup.com. And we thank you all for your time and definitely your engagement. And hope that we are able to have you at our next webinar. And thank you to Holden Payne and to Jean-Simon Michaud. And have a great afternoon.